Okay, so we're going to be talking about a really interesting topic called related rates. And if you've covered something called implicit differentiation, then this will make a lot of sense. But this is where, in the real world, we'll see a lot of applications of calculus. And I think that you'll kind of notice what's going on here. But we'll take a look at some practical applications of it, and then in another video we'll talk about some actual um, places where you might be able to apply it in the real world. But consider, let's say that you have some kind of oil spill in, let's say, the Gulf of Mexico. And so let's say, this is the Gulf of Mexico, and the oil slick is just expanding. Okay, it's expanding in all directions. Well, there's different things that you can analyze from this, the rate at which it's expanding and stuff like that. But that right there involves calculus, and that involves this concept here of related rates. And if you're taking any kind of, accreditation exam on calculus, you're gonna see a related rate problem. Okay, it's just nature of the game there. So let's go ahead and take a look at a couple of examples, three to be exact, really basic examples, but some very familiar formulas. So if you have done implicit differentiation before, this is no different. I call it, taking the X treatment and the Y treatment, but in this case, what you're going to do is you're going to state that everything has a rate of change associated with it. So if you take the derivative of x, you also need to say x prime. If you take the derivative of y, you need to say y prime, because everything has a rate associated with it in this case. And you'll see that very quickly. You treat every variable as a variable, something that you could take the derivative of. So let's go ahead and take a look at this example. Number 1. All right, so it says, suppose that the radius r and the circumference c equal 2 pi r of a circle are differentiable functions. So that means that both sides of the equation we can take the derivative of. Write an equation that relates dc dt to dr dt. Now, I am going to call this right here c prime, capital C prime, and I'm going to call this here r prime. Okay, just for the sake of it's easier to write, but this is the Leibniz notation that surely you've heard of before. So if we take the derivative of c, it's kind of like an x. The derivative is 1. So it's 1, but you got to say c prime, because you have to explicitly state that you took the derivative of that. Okay? This is all about implicit differentiation. Okay? So we must say c prime equals. Now 2 and pi, those right there are coefficients. They're constants. Okay? But r is a variable, and if you take the derivative of r, it's like taking the derivative of x. It's just 1, but you have to state r prime. So when we write an equation that relates dc dt to dr dt, that's this right here. dc dt equal 2 pi dr dt. This is the same thing, okay? These two are synonymous. They are the same thing. Different way that you can express. One of them is prime notation. The other one is, of course, Leibniz notation. But there's nothing to it. Later on, when you apply it, you're actually going to plug in numbers for this, and that's what makes it a lot of fun. They're actually really interesting problems, and I think quite fun to solve, because sometimes they can be kind of cryptic in terms of it's a puzzle you've got to figure out. So let's take a look at a couple more examples. Number 2, suppose that the radius r and the volume v are equated and such that v equal 4/3 pi r cubed, which is the formula for the volume of a sphere. And they say this is a differentiable function of time t. Write an equation that relates dv dt, the rate of change of the volume, to the dr dt, which is the rate of change of the radius. So think about it. As the radius, say that you've got like a balloon that you're inflating. As you blow up the balloon, let's say it's a spherical balloon, the radius is expanding and so is the volume. So if you can picture that balloon, it's getting bigger and bigger and bigger over time as you blow up the balloon. Okay, so that's kind of what's going on here, and that's a practical application of this formula here, for example. So if I take if I take this formula here, I'm going to say, well, using my notation, this right here is v prime, and this right here is r prime, okay? So I take the derivative just like I would anything else. So I'm going to first say v prime, because that's the derivative of v. And then if I look over here, 4/3 and pi, this part right here, that's a constant coefficient. So I bring the power down. So I'm going to have 3 times 4/3 pi r to the, take away 1, r to the second power. And then because I took the derivative of r, I need to say r prime. So can you clean this up? Yes, of course you can. The 3's cross out through division. All right, and you are left with something that looks like this, which is 4 pi r squared r prime. And this right here is your v prime. It is also your dv dt, in other words. So you could say that this is also 4 pi r square dr dt, which is your dv dt. Okay, they are the same thing. One of them is in prime notation, the other in Leibniz notation. Okay, and let's take a look at one last example here, just for good measure. I think it's good practice. All right, this one says the area of the base B and the height h of a pyramid, all right, are related to the pyramid's volume v by the formula v equals 1/3 of the base times the height. And then it says, how is dv dt related to, and this was cut off for some reason, so let me write that in. How is dv dt related to dh dt if the base b is constant? Okay, so we have to hold the base b constant. So I'm going to highlight that here, that 1/3 and b are constants. So we don't need to take the derivative of that. We only need to take the derivative of the v and the h. And this right here tells me that this is v prime, and this I call h prime. But other than that, it works the same way. I will say and start off with the fact that v prime, the derivative of v, because it's just 1, equals 1/3 of the base, which is constant, times the derivative of h is just 1, but we must say h prime. And so that's pretty much it. And the only other thing that I can do is write it in Leibniz notation to say that dv dt is 1/3 of the base times the dh dt, which is the rate of change of the height. So the rate of change of the volume is dv dt, the rate of change of the height is dh dt. And that's how these are related. Okay, there's different ways to express it. Again, prime notation or Leibniz notation, but to quote Shakespeare, a rose by any other name would smell as sweet. It just depends on, what book you're using, who your teacher is, for example, but they are basically saying the same thing. So in the next video after this, I'm going to actually look at some applications of these kind of problems. But if you're just looking for formula help, this is probably sufficient. All right. As always, I hope this video was helpful. And remember, like and subscribe.